topic, validating system software with ARM FVPs. This was a requested topic when I had done last month technical webinar on debugging issues with bootloaders, and one of the customers had suggested me to take up this topic, so here I am. So it will be a pure technical webinar, no commercial, nothing, no product promotion, nothing. This is basically to educate our customers on what the technologies or software solutions which are offered by ARM and which can help the customers or users to develop the project or bring the product to the market on time. So basically the keyword here is time to market. And with the same keyword only, we have to start up this session because we are talking about fixed virtual platforms. So what are these virtual platforms? As your name suggests, virtual platforms. Basically, virtual means, as you know, there is nothing physical world involved here. It's all virtual, like Linux. All applications run in its own virtual space. It's not on the physical space. So similarly here, we have this virtual platforms where it will help you to test your code before your hardware is available. So first we'll see what are FVPs. So FVPs are nothing but the system models. So this basically will help you to develop your software, analyze your software, debug your software even before your actual hardware is available. So why, as I told, we will start with the keyword time to market, right? So we will be stressing more on this particular sentence, time to market, and we will correlate that with how FVP can make it achieve that, bringing the product to the market on time faster. Because the market is a competitive market, whoever releases the product to the market will occupy the market, or in other words, will have maximum profit or gain on market share. So they are nothing but the complete simulations of an ARM system. So you can entirely simulate your entire embedded system. So embedded systems, as you know, what is an embedded system? It can be a processor, it is attached to a peripherals, it can be on chip, it can be external peripherals, external memory, some external peripherals, like that. So this entire embedded system. So the entire ARM system can be simulated. So including the processor, it can be a memory, and it can be peripherals. Okay, and FVP gives you the programmer's view. Basically, when you are programming the code, what is that you see? When you are programming the code, you never get into the architectural level, like how on the architecture level or how on the processor level this peripherals perform, or how this code is performed by the processor. So this gives you the programmer's view, the way you write your program in C, or if some people, to get the better code or better control on the processor, or to get a better optimization and better performance, they also code it in assembly. So whatever it is, the view, whatever the programmer's view is there, that you can simulate it in FVP. Okay. So this functional behavior of the model can also be equivalent to the real hardware. So sometimes there are some simulation models offered by ARM. Earlier they were there, which is cycle simulation of cycle accurate simulation modules. So some simulation models, whatever the timing or whatever you see, the performance, the same thing you can see it in your actual hardware as well. So why FVPs? So first we saw what are FVPs. Now we'll see why anyone has to go for the FVPs. So the reason is here again, a keyword, what we started with the caption, time to market. So the current scenario, how it works is, if the team is working on a particular product and they're not aware of FVP, or they're not using any FVPs, then what will be the scenario? So, you know, hardware development, finalization of the hardware, finalization of the BOM, bill of materials for the hardware, everything takes time. Even some issues is in the hardware, again it has to be redesigned, and again the final BOM has to be generated. So this is a long, laborious process, and this takes time, and the hardware team takes some time to develop the hardware and give it for fabrication, or until the final hardware is made available. So till then the software team has to sit idle. what that they may based on the project requirement, they may still develop the code, but they don't have the option of testing the code where they will test because they don't have the hardware. So they have to sit idle until the hardware is made available from the design team or the hardware engineering team. This will happen, this will, since they're sitting idle, it's a waste of time and you're not able to get the product to the market in time, means you're not able to get the market share or capture the market. So how FVPs will help is the both the process can go parallelly. The software development and the hardware development both can go parallelly. So whenever your hardware development is in process, software team can develop the code and they can still test the program on the FVP, fixed virtual platform simulation modules, and they can ensure that their code is working on the simulation model, probably with some modifications, or if they're lucky enough, the entire code may work directly on the hardware for fine tuning and final optimizations. So this way, the development time will be reduced by half, almost 50%, when you are using the fixed virtual platforms. Okay. So software engineering team work on application firmware that we know already as such. In cases where large team is working on generic device support, models remove the need for the large number of hardware targets. So specifically, this case comes usually at the time of POC stage. Many might have faced it. Before the starting of the project, you will have a lot of devices. Like now, if you want to go to purchase mobile, you'll see a lot of brands, various brands. In the brands, there are various models. Again, based on the memory, octa-core, quad-core. Again, based on the camera quality, battery backup, whatever it is. So there are we have a different varieties of the smartphones available in front of us, and we have to select one which suits our requirement or whatever we are looking for. So similarly happens for POC. In POC, there are a lot of embedded processors available in the market, so you have to be very particular about what is the actual project you are looking for, what is the actual product, and what is the required peripherals for it to for that project development, and which specific device has those peripherals and which can give you the better optimization and performance in terms of processing speed and all. If it is IoT application or if it is processing of some data from the sensors, they have to process a lot of data at a very high speed. So based on that, the team, it's really a difficult, tough, it's a challenging task for the team to select the required processor for your application, which goes as part of the POC stage. So here usually we will be doing the trial and error basis, like we'll select just for testing purposes, not that you will have to physically purchase the device. You can use FVP, they will not have the requirement of purchasing these devices physically and spending money or shelling of the money for many of the processor devices. So here you can select any device that you want and you can test how the code works on that specific processor on the FVP, and you can decide on it. So this will certainly ease the POC stage. With the processor, memory, and other peripherals modeled within an FVP, you can get a good analog for how software will execute on a physical device. So, with the help of executing your code, your target application on the FVP, you'll have a good understanding on how your software will actually perform on your physical device or your actual target. Okay, so FVPs offer a lot of out-of-box solutions for basically for productive software development, because as I said, this is specifically advantage for software development team who are developing the software code. It can be firmware, it can be device driver, it can be peripheral driver, it can be anything. So here you can see we have FVPs for ARM system guidelines platforms. We have actually mobile and infrastructure platforms. Basically, we have FVPs for all the ARM processor codes except ARM 7, ARM 9. We have FVP for Cortex A, R, and M. For A, we have 32-bit and 64-bit FVPs as well. So we have library of FVPs for all the processor cores, which have been released by the ARM. Okay, and all this FVPs actually designed by ARM are based on some versatile express boards. Earlier, ARM used to offer VE boards, we call it as versatile express boards. And these FVPs, fixed virtual platforms, were designed specific to simulate or model that specific board. As the name suggests, fixed virtual platform means this particular simulation model cannot be tweaked or cannot be modified, cannot be customized as per your target, but it can be used to simulate the entire processor features. What I mean is, whatever the peripherals available inside the specific processor can be still simulated. Okay, it can be watched out, it can be a WT, it can be wake up interrupt controller, it can be vector interrupt controller, it can be anything. It can be any so it can be any peripheral which you can simulate it with the virtual models. Now coming to the question, how about the peripherals? Peripherals when comes into picture when you are using a microcontroller or you are using a processor, like you are using a processor based on Cortex-A or you are using a microcontroller based on Cortex-M. That time, how do you simulate the peripherals? So there actually comes based on those models are based on the some specific development board what ARM has offered till now. So ARM still offers MPS2. Here we have also now MPS3. We also have MPS4. MPS2, quickly I'll tell you, it supports all simulation. We can do it for it's basically for your software verification validation or pre-silicon verification validation. You can do it for all Cortex-M devices. We have MPS3. MPS3 comes with a high capacity FPGA where you can program all the Cortex-M cores and some selected Cortex-A cores. Then you have MPS4. MPS4 supports all Cortex-M and all Cortex-A 32-bit, 64-bit processors. It has a high capacity FPGA. MPS4 can be specifically used for AI and ML application workloads, specifically targeted for IoT applications. So there are a lot of cornerstone FVP models. I'll show you at the end of this presentation the page on the ARM side. So those models are specifically implemented for IoT, for specifically AI and ML applications. Okay. Now, why anyone has to go for FVP? Okay, so FVPs actually can be downloaded as a standalone, or it can be bundled with an IDE like Kyle MDK or a ARM Development Studio IDE, and you can use that for debugging your code. But if you're running a simulation model in the standalone mode, you'll not be able to debug the code whatever you're running on the model, because there is no ID associated with it, and you'll not be able to simulate any registers or anything of the processor core registers or peripheral registers. So my suggestion is you always use the simulation models which comes bundled with the MDK license. MDK is for specifically for Cortex-M devices, including ARM7, ARM9, and DS is for Cortex-A and R for 32-bit, 64-bit devices. Okay, why anyone has to go for FVPs, why anyone has to invest in FVPs is software cost is increasing. So we know that the cost of developing the quality software increases rapidly as the complexity of the IC designs increases. Now you see there are a lot of SoCs which has multiple processors, it has different processor cores, it has 100 numbers of IP cores, IT blocks and everything. In such cases, developing the software is really a challenging and a complex and a laborious task, and so a lot of the company has to invest in hiring a lot of software engineers who can do this task or complete this project. So virtual platforms are specifically used for software development. So as I said, ARM still these virtual express FVPs are given as part of DS because development studio is a single universal toolset which supports all ARM processor cores. So if anyone wants to work on develop a project based on any ARM processor core, then I would suggest DS. If it is specific for Cortex-M, then you can please go for Kyle. So DS offers a lot of virtual express based FVPs, fixed virtual platforms. You can see them. I'll show you that as a demonstration. I have a demonstration of an FVP with a DS, which I'll be showing for Cortex-A9. So these are specifically developed for versatile express boards, which ARM used to give, which has been now obsolete, but the models are still there. So what is a typical virtual platform flow? So first we will start up with, um, we'll start off usually, because the team is new to FVP. What they do is they usually try to use the sample project given by the ARM, try to understand or use that as a template to start up their actual project as well. Okay. And the FEP is so powerful for Cortex A that you can also boot the OS on it. Like Linux OS can also be, we can also simulate the even OS boot or the Linux kernel as well. Okay. Then you can modify your project as per the whatever the your actual target requirement is there. You can also try to see if you can configure the simulation model for mapping as per your target application. And you can also do the debugging and tracing also on the simulation model if at all you're using with MTK or DS, because you'll get the GUI and you can see the powerful debugging capabilities. Functionalities are included in both DK, MTK, and DS. So finally, when the code is tested on the simulation model, the final tuning can be done at the final stages of the project with your actual hardware. Okay. So these are the one which I was talking about. So this versatile express is what we have simulation models. We all have for A class, M class, and even for R class. So this is you can see here IO access, virtual IO, peripheral model, and peripheral model. So this I'll explain you what it is. Basically, when you write here, there is one more block will come. I'll show this information on the site. You'll be able to understand easily. Um, for now, just remember whenever you want in your application, you want to simulate any peripheral like timer peripheral, UART peripheral, or a DMA peripheral, which can be on chip or external. Then we'll be writing in our application, we'll be writing the peripheral drivers. Those peripheral drivers in turn will call the registers which are part of this simulation models. And then by writing to those registers or reading those registers, the simulation of your application and the models can be achieved. So I'll explain you that at the end of this slide. So virtual prototype, debug and trace with ARM DS5 or DS. DS5 is now superseded with DS. All the features of DS5 is included in DS. So what all you can do bare metal trace for ARM v7, v8 core. We can do the debugging. Debugging is yours. You can do single stepping, instruction stepping. So stepping is that is stepping through even your C code like this. You can see this is your C program. You can step through, step into. Similarly, you have instruction stepping. This is basically for your disassembly code, or it can be your assembly code. So similarly, you can also use this for streamlining. Streamline is basically to if you want to optimize the features of your application, or if you want to see how the processor is executing your application like that, you can see that in the uh, DS streamline. Okay. So here you can see all, if you have any for Linux, basically if you want OS specific or thread specific, all those information you can get the information, because this streamline is not virtual concept. Is basically you're connecting the hardware and you'll be collecting the counters is basically, this is usually to know the performance of your application, how processor is executing. So you want to see number of cache miss happen, hits happen, or this how MMU is performing. It can be anything, any peripheral, how TLB caches are performing, translation look aside buffer, memory management units. So all these are, for all these units, ARM has implemented certain counters which are there in the processor core itself. This streamline will help you to read those counters and show you the performance on how the processor is executing your code. Okay, so I'll come to here now. Okay. So basically, now we have ARM virtual hardware, which is part of this. For FEP models are now part of ARM virtual hardware. Okay, these provide the accurate simulation models for Cortex MCPUs and Corstone 3X. So Corstone is all your simulation models developed for MPS boards with the various processor combinations. So you can see here, these are the available simulation models. We have for a combination of M85, U85, C55. Mali is a graphics processor from ARM. So similarly, you have it for if you want M55, U55. U55 is like your NDP, numerical data processing kind of like a co-processor you can use. So M55, M85 applications are specifically used for IoT applications, specifically for simulating AI and ML workloads. Because M55, M85 has a helium technology implemented in their architecture, which is specifically aids or facilitates or make this processor suitable for AI and ML workloads. So similarly, we have for M55, we have M7, M4, M3, M0 plus M0. Okay, so don't worry, I'm showing only ARM virtual hardware, and madam was telling Cortex A also, she's only showing M. These are the ARM virtual hardwares which are available as part of Kyle MDK. Okay, so Kyle MDK, as I suggested, it's only for Cortex M based devices. So I'm showing you this. Okay, so how this simulation model works on. So this is, consider this is your user application code. You have RTOS, it can be free RTOS, CMC RTOS too. So we have this free RTOS, or it can be RTX RTOS, which is part of ARM. You have event recorder. Event recorder is basically the feature of Kyle IDE, which helps you record the events, how the RTOS is performing, specifically RTOS kernel or scheduler, how it is performing when it is task switching, relating to the events, everything, binary semaphores, queues, all those information you can find it out with the event recorder. So let's come to user application. You have a demo or some demo application which is controlling some switches or LEDs on the board. And you have some applications. So suppose this application is written for voice recognition, which is for basically for artificial intelligence. Let's take Alexa. So this application is written for voice recognition. So how do I test this application on simulation model? So I'll select a simulation model which is apt for my application, and then I simulate the IOs through the VIO. We can see this virtual IO. Similarly, this voice recognition, this I can use it through VSI. Okay, so what is this VIO? VIO is virtual input output. So input output, it can be through IO ports. It means you usually control it through IO ports only, and we usually configure the registers associated with those IO port to make the switch on or off, blink the LED on and off, all those. And VSI is specifically for IoT related application. If you want to stream, if you want to simulate any audio, video, or any some data packets or data streaming application, which is specifically found in IoT application requirement, then VSI can be used. It has 8 channels, so you have 8 different channels interfaces which you can simulate the other components which are required for IoT. So if I get into VIO in detail, this is how it comes. Excuse me. So we have here, this is the application on the Cortex M side. So this is basically the application what I have written in for Kyle. In Kyle ID, I have written this software application. This is my actual application. Okay, this application uses the CMC driver. Suppose I want to configure say GPIO port, which is connected to the LEDs. So peripheral driver, I'm using that LED driver. So here, how do I tell this? How do I simulate this LED driver on the simulation model? Is with the help of Python script. Okay, so whenever this VIO peripheral driver writes or reads some registers, VIO has some memory mapped registers. When VIO peripheral driver writes to those memory mapped registers, read or write, then the associated Python script command will be executed. So this script, Python script, is available, it's stored locally on your system. Or this Python scripts are downloaded as part of the simulation model, what you select. And this is how it works. So Cortex-M first initializes the VIO peripheral. Suppose I want to set one specific LED output A. So how do I set? I usually write some value to the register. Usually it will be 1 to a specific register bit to make the LED high. So this will capture the output A. Similarly, I want to read. So this will load the value. As soon as I give the read input, so it triggers the read to the specific register B, and this will load the value of the register B, and it returns back, and your application can read the value. So this is how you can simulate your code on the simulation models. Now coming to virtual streaming interface. So virtual streaming interface, as I told, it can be used to simulate the interfaces, streaming interfaces. Please remember the word streaming, where there is a continuous flow of audio, video, information, or any various sensors information. This is typically required for IoT and ML applications. So this also works the similar concept as I said. This is also again through your Python script only. So this FEP model has this memory mapped peripheral available. So there are this particular 8 channels. They have a different registers which are associated. These are memory mapped, and you can write to those registers or read those registers to do the simulation or to add the simulation support for these streaming interfaces. Okay, this is about MDK. Now coming to Development Studio. So in Development Studio, this is the Development Studio. As I was telling, ARM Development Studio, this was DS was superseded by DS. This is Eclipse based only still, but the interface is a bit simple in comparison to DS5. So here there is a lot of sample projects which you can import it. If you go to the DS program installation folder, you'll get a lot of these sample projects. I have imported one Cortex A9 based application, which simulates the firework example. Means it simulates. It's basically your fireworks for crackers when you burst, how it twinkles in the sky. So that they have simulated on this simulation model, which is FEP A9. So to quickly, I'll show you debug configuration, because here you'll be selecting the simulation model or you'll be using any JTAG debugger for the model. So here I have selected VE Cortex A9, Virtual Express Cortex A9, and I'm launching the model. So I'm not connecting to any hardware here. Okay, here I will specifying what is the file, that is the final output file, debug final output file, which has a debug information, which is AXF file, which is the similar to MDK and DS. At this point, let me tell you, the compiler, ARM compiler, which comes as part of MDK and DS, is the same. Okay, so here, and debugger nothing. And when you click debug, it's already running. Let me stop this. Debug. So you can see here, this is one interface. This comes up, and you can see here it has user switch on, user switch 1, boot switch 1, and there is some LEDs 0 to 7. So this is a fixture virtual platform which is simulating the virtual express board of ARM for Cortex A9. So this FEP model is been developed for that board. So now you can see my program comes and starts at the main function, where first is UART initialization. Okay, so here you can do the single step, You can see the registers. Setup screen. So here this is the screen, and so you can do single step here. All the registers you can see. You can see the processor specific registers, core registers. I mean, memory. If you want to watch any memory location, you can see disassembly. Whatever the code I've kept, the program counter at C, that's equivalent disassembly. I can see. So all this, now I'm running this code Fireworks application on the simulation model. Okay. So once I run, what happens? Stop time breakpoint. Okay. So I put a breakpoint to show you registers and all. Let me remove this breakpoint. And it goes. So this is the application which they have simulated on Virtual Express. This only shows development tools for multi-core debugging and trace with the fireworks simulation with the helicopter. This is just a fancy thing, but the main thing is to show you, see the LEDs are blinking here continuously. Okay. So this is the Virtual Express platform for Cortex A9. The one what I showed on the ARM site is specifically for Cortex M, which is AVH. So for that you have to use this Kyle. I don't know whether I'll be able to show you this, but I'll show you Kyle. Let me stop this. Okay. Basically, with the pack installer, you can download any example projects which are developed for MPS2, MPS3 boards, MPS4 boards. These are like versatile express boards only, but microcontroller prototyping system boards, which can help you prototype or test your program for various Cortex M processes. Okay, but if you want to simulate any of the model, you have to download any of the model from here. Okay, and there is a guide also. These models are part of Kyle MDK already. Okay, I can show you that. So you can see these are the models: Corstone 330, Ethos, M3, M4, M7, 23, 33, 35, T52, M85, all this. These are all the models. These are the reference guides or the user manual. It will tell you how you can run those models in Kyle. Let me see if I can show you. Okay, if I select ARM, suppose if I take MPS3, so there is only sample projects. These projects are specifically for, this is a software application code for your MPS3 board. Like I can use it as a demo application to test how the MPS3 board performs. This is using virtual. This is MPS SSC. This is actually the board. This is not the simulation model. But for simulation model applications, if I go to packs, do I get anything here? or probably if I use any of these Blinky projects, because I don't have the board now, but I should be able to still simulate the application. If they let me check out. Copy resource documents. Okay. MPS3 IoT. Okay, let me give it a try. Documents, boards, MPS3, Blinky. Oh, this is with the hardware. Here you can select ARM V8M debugger. These are the models, whatever I showed you, which comes as part of Kyle MTQ. Okay. Right. Oh, I have to put compiler file. Okay. Anyways, I wanted to show you that you can select the memory models here in the debugger. Okay. Compiler file I have. Now one is integration. Compiler file is there. It is not showing there. Compiler file I have integrated already. Anyways, I don't have that board to test also. Okay. I'll try to fix it up later. Okay. So this brings me, okay, I wanted to conclude that part. So in summary, fast models and FVPs enable early engagement with the latest processor. Means ARM keeps releasing the latest processors with the features specifically targeted for automotive or medical or IoT, whatever. So even before the silicon vendors, means even before the semiconductor vendors come with IC or a processor core, you can have access to that specific processor core, and you can develop the software on it. Latest ARM IP support enables early design started. That is the key caption. We started time to market advantage. And it's also FEP is an excellent tool to learn about new IPs, as I said. So this brings me to the end of the documentation. So this is in summary what FEPs does. Okay. Now so any of you has any question? You can ask me question now. because many of the customers are not aware that ARM has this FVP and which will help you for simulation of your code. So no questions. If you have questions, or I think Kalpak already have my mail ID. This is my mail ID, geeta@jesusmspl.com, and phone number 9342756672. Please reach out to me. You have any information you want, or even licenses you want, or any support on ARM processor core, anything on the simulation platform or development facing any issues, I'll be available. I have more than 2 decades of experience on the ARM architecture, ARM technology, Kyle, DS, everything, RTOS, middleware, boards, JTAG, everything I can support. Is ETM an add-on feature for low-end devices? Kalpak, ETM is embedded trace macro cell, and basically this is implementation defined, means silicon vendor like NXP, ST, or Broadcom, or whoever is developing the processor cores or microcontrollers, they will decide whether ETM has to be implemented in their device, microcontroller or core. Basically, the reason is ETM occupies lot of transistor gates on your silicon die. So, and it will also make the cost of the device higher. I mean, at a higher side. So, ETM implementation for lower end device is impossible. And it will be like an overkill for it. When we use the word lower end device, they have been specifically designed for lower end applications. Correct, simple applications. So ETM can be used for a device which can withhold it, which is capable of holding ETM. So low end device, no, ETM is not an add-on feature. So Kalpak, you have any questions, you can send me an email. We already have a communication. So looking for it on additional debug for low end in simulation. ETM, if you want, probably you have to select a device which has ETM. For lower end devices, ETM, even I believe even silicon vendors will not prefer ETM for lower end devices. Like if you see ETM and all, if I take example of M0, M0 Plus and all, there are lower end Cortex M devices. ETM is overkill for them. But ETM can be an option for M3, M4, M7, M23, M33, for all those. So it is up to the silicon vendor to decide. After this webinar, you can call me. Or probably at 4:30. I have some, after this webinar, I have some work, urgent work. I have to send one proposal. So you can call me at 4:30, Kalpak. I'll be available. Okay, team. No other questions. Thank you. Thank you for your time. And I'm glad that photo registrations we got. All the team is here. Thank you so much. Thanks for your time. Wish you a pleasant evening. Bye-bye.